DP Year 11 exams, May 2017, paper 2. Question 1. Two IB students carried out a project on the chemistry of bleach. Right, so a bit of information here. The bleach contained a solution of sodium hypochlorite. Now this is an ionic substance because there's some sodium there. So it consists of sodium plus ions and hypochlorite minus ions. And in fact, they were told then the students determined experimentally the concentration of hypochlorite ions, HClO- in the bleach. This is the experimental procedure. 2 steps. The bleach solution was first diluted by adding 25 centimeter cubed of the bleach to 250 centimeter cubed and making up with deionized water. This is a 10-to-1 dilution, so we need to remember that here. It's a 10 or a 1-to-10 dilution, we should say 1-to-10 dilution, because it's 25 goes into 250. This will help us later on, so we'll just highlight that 1-to-10 dilutions being used so that we don't forget. Then 25 centimeter cubed of the diluted solution, the diluted solution, was then reacted with excess iodide in acid. There's the iodide, there's the acid, and it reacts with the hypochlorite. You'll see that 1 mole of hypochlorite produces 1 mole of iodine. So that's a 1-to-1 reaction. We could put that in there. 1 mole of that produces 1 mole of iodine. There we are. Take that back a bit. 1 mole, 1 mole. So that gives us, this just reminds us exactly what's going on. 1 mole of hypochlorite produces 1 mole of iodine. And then the iodine formed is titrated with 0.1 mole sodium thiosulfate, and this is the equation. 1 mole of iodine reacts with 2 moles of thiosulfate. So here we've got an equality. We've got 1 mole of iodine. We've got 2 moles of thiosulfate. So it's a 2-to-1. So overall then, 1 makes 1 mole and 1 mole requires 2 moles. And so 2 moles of thiosulfate are equivalent to 1 mole of hypochlorite. Okay, this is information about how the experiment works. Then we get to some questions. The following data were recorded for the titration. So this is a typical titration table. Let's put in the differences. Final burette reading, initial burette reading. So the difference here is 23.95 is the titer. It's how much was added. This one is the difference between these two, which is 22.05. Now you should notice that this is much larger than this. Ask yourself why. Well, the answer is this first titer is what we always do. We do a rough titration first, and then when we know more or less whereabouts the answer is, we then start to do accurate titrations. And here the two values, 22.15, you'll see these two values are concordant values. They are values within 0.1 of a centimeter cubed of each other. So these are the two values we would use when calculating the volume of 0.1 mole of sodium thiosulfate required to react with the iodine to reach endpoint. It's the average of 22.05 plus 22.15 all divided by 2 to get the average. And you can see that equals 22.10 centimeter cubed. Let's format it nicely. That's good. So there's our answer to question 1. Now the next part, question 2, part 2, calculate the amount in moles of sodium thiosulfate that reacts with the iodine. Well, this is the volume of sodium thiosulfate, and moles equals molarity times volume, mv. Well, the molarity is 0.1. The volume in litres is 0.0221, and that equals 0.00221 moles per litre. Now I suggest you always put down the working when you do a question like this, because if you get the final answer wrong because you press the wrong numbers in the calculator, at least you might get a mark for the process, if you show that you know what the process should be. Now the next part of the question, calculate the concentration in moles per litre of hypochlorite ions in the diluted bleach solution. So this is after the dilution. So now remember, this is where we need the fact that 2 moles of thiosulfate reacts with 1 mole of hypochlorite. So actually I've done this wrong, haven't I? I put moles as MV and I've put the concentration. I don't want the concentration, this is just the number of moles. Good job we spotted that one. So now we've got the number of moles of sodium thiosulfate and the number of moles of, from this, the number of moles of iodine, the number of moles of hypochlorite is half of that. So this is simply, I can't get me mouse to come over here. There we go. That's what we want. Moles equals 0.00221 over 2. 0.001105 moles of ClO minus hypochlorite. We don't want the moles, we want the concentration. So that's the number of moles. So the concentration, the molarity, will equal the moles over the volume. So it's 0.001105, and this is in 25 centimeter cubed, divided by 0.025. Maybe a calculator's handy here. 0.001105 divided by 0.025. This gives us 0.0442 moles per litre. The concentration in moles per litre of hypochlorite ions in the diluted bleach solution. Then we calculate the concentration in moles per litre in the undiluted solution. Well, you've got the concentration in the diluted solution. Remember we used a 1 to 10 dilution, so in the concentrated solution it will be 10 times more concentrated. So we're just going to go straight to concentrated solution, molarity equals 0.442 multiplied by 10 times, I'm going to use the computer times, 10 times, and of course that equals 0.442. And that is the end of question 1. Question 2, all about magnesium. First of all, it just asks you to define the term first ionization energy. The energy required to remove 1 mole of electrons from 1 mole of gaseous atoms forming 1 mole of single charged gaseous ions. Emphasis all the time on gaseous. The energy required to move. Okay, so that covers all of our bases. It didn't take us long to type that if we know what it is. So we can give an example. Mg plus gas. No, what's wrong? It's Mg gas goes to Mg plus gas plus 1 electron. So this is the equation for the statement definition. Then they were given some successive ionization energies of magnesium, so that's one after the other, first, second, third. Explain why the third ionization energy is much greater than the second ionization energy. Well, so we're stripping electrons away from magnesium. Magnesium has got an electronic configuration, a simple electronic configuration, 2 electrons in the first shell, 8 in the second shell, 2 in the third shell. So if we remove removing 3 electrons, the first 2 electrons are removed from the outer shell. But of course the third electron has to be removed from a shell that's closer to the nucleus and hence held more tightly. More energy is needed. Much more energy is needed. And you could say, due to the higher electrostatic force between the nucleus and the electron. That last part's probably not needed at all, but certainly everything else covers our bases there. Question 3. Describe. Describe, that means what does it look like? We need to describe it. Physically describe what it looks like. Okay, so we have several series of lines. I appear to be getting formatted. Yeah, what's going on? Why am I being formatted with underlines? We don't want underlines, do we? No, of course not. Several series of lines, comma, each series converging to a higher or high energy limit. Several series of lines, each series converging to a high energy limit. There we go. That describes what it looks like. The computer wants a hyphen, high energy limit. Outline how this spectrum is related to the energy levels in the hydrogen atom. Well, each series corresponds to energy emitted when excited electrons, I could say fall back, or the correct word is relax, down to lower energy levels. So relaxing of an electron emits energy. Each series corresponds to energy emitted when electrons fall back to lower energy levels. Series 1, for example, or should we say the first series in the ultraviolet, the first series shows relaxation down to n equals 1. This is in the ultraviolet. You don't know this information, but I'll put it in anyway. The second series shows relaxation down to n equals 2. This is in the visible. This is the visible one. Visible series, etc. Maybe, as this is not just a mark scheme, we want you to know this. Should we include a little diagram? Let's insert a little diagram here, just so we can remind ourselves what the what the hydrogen spectrum looks like. Documents. Let's go into books, atomic images, H spectrum, insert. Oh, that's not the one we wanted. Should take us back to the same place as well. H series, H spectrum. That's 2H spectrum, JPG. Well, this is the visible spectrum. You see 1, 2, 3, 4, 5. This is the hydrogen visible spectrum, not the full spectrum. So let's just make sure we understand that. This is the H visible spectrum, showing only the Balmer and that's to n equals 2 series. Okay, let's move on. Question 4. The boiling points of the isomers of pentane are shown below are 10, 28, 36, but not necessarily in that order. Identify the boiling points. Well, all three molecules have got the same formula, chemical formulas. They're pentane, C5H12. So they've got the same relative mass. None of them have any kind of different atoms, electronegative atoms, so they cannot undergo or cannot experience dipole-dipole interactions. Therefore, the only force that holds these atoms together, or to themselves, is London dispersion forces. London dispersion forces depend upon the available surface area as well as the relative mass. The relative masses are all the same, so the available surface area is greater in A than it is in C, and B is somewhere in between. So A is going to have the highest boiling point, 36, B is going to be intermediate, 28, and C is going to be the lowest, 10. So we need to identify, we've identified the boiling points. Let's give a reason. Okay, the intermolecular force, the only intermolecular force, is London dispersion. This depends on relative mass, in this case the same, and available surface area. Molecules with more branching have less surface area to volume ratio and lower London dispersion forces. Alright, so C is the most branched. C is the most branched, and we'll have the lowest boiling point, etc. Question 5. We need a phosphine. IUPAC name phosphane is a hydride of phosphorus with the formula pH3. Draw an electron dot structure of phosphine. Well, I can't draw it with the computer very easily. I suppose I could draw screen draw. No, let's not draw screen draw. Let's insert a picture just so we can see what phosphine should look like. We want to go up back to bonding, images, Lewis structures, PH3, there we are. Okay, so there's the Lewis structure, electron dot structure of phosphine. Now how do you get there? Well, you get there because phosphorus is in group 5 or 15, so it's got 5, these are the red ones, 5 electrons. Each hydrogen provides 1 electron, there's the blue ones, so there are 4 electron domains, and only 3 of them are used for holding hydrogens. Outline whether you would expect the bonds in phosphine to be polar or non-polar, giving a brief reason. Well, in this particular case, you need to know the electronegativities. So if you look up the electronegativities in the data booklets, you'll find that P and H have the same electronegativity. Therefore, or so, the bonds are non-polar. There's no reason for the electrons to be pulled one way or the other. They're non-polar. But it requires us to look at the electronegativity values, and they're both given in the data booklet as 2.2. Phosphine has a much greater molar mass than ammonia. Explain why phosphine has a significantly lower boiling point. Okay, so you would expect the London dispersion forces in phosphine are greater than ammonia, which you would expect would lead to a higher boiling point. But ammonia can hydrogen bond to other ammonia molecules. Ammonia can hydrogen bond to other ammonia molecules as the lone pair is attracted to the hydrogen atoms which are attached to the highly electronegative nitrogen. And hydrogen bonding is a much stronger force in small molecules. So the answer is, notice in this answer we also refer to phosphine. Phosphine cannot hydrogen bond. London dispersion phosphine has got London dispersion forces. It's also got dipole-dipole interactions. But the hydrogen bonding, H bonding, so we should say really maybe H bonding is much stronger than London dispersion forces, LDF, and dipole-dipole interactions in small molecules. Let's move on. Phosphine is usually prepared by heating white phosphorus. Now here's the equation for the reaction. One of the allotropes of phosphorus with concentrated concentrated sodium hydroxide. These OH minus ions come from sodium hydroxide. Sodium hydroxide's got the formula, NaOH. Why don't we put Na in here? Well, because the Na, it makes it ionic, so that when it dissolves, the sodium ions and the hydroxide ions go off individually. They are 100% dissociated. The first reagent is written as P4, not fill P. Why is that? Well, that's because this represents one molecule. P4 represents a molecule of phosphorus that contains 4 atoms covalently bonded together. 4p, however, 4p would represent 4 individual phosphorus atoms. Very important to understand the difference. You would never write 4p. 4p may appear in an equation, but it certainly wouldn't be written. The 4 is a coefficient. Okay, impurities cause phosphine to ignite spontaneously in air to form an oxide of phosphorus and water. 200 grams of air was heated by the energy from the complete combustion of 1 mole of phosphine. And we're told that standard enthalpy of combustion for 1 mole is 750 kilojoules. So if we use our equation, E equals mc, I need a delta here, let me have a delta, mc, there's a delta, mc delta T, well, the energy is, where is it, 750 kilojoules, and we're given, this is in what, the specific heat capacity is 1 kilojoule per kilogram, so it's times 1, it's easy, times, and delta T is what we're trying to find, the change in temperature. I've written that wrong, haven't I? I've written that wrong, sorry, it's E equals, get that off there, I was going to say, let's put it underneath. E, the energy, 750 kilojoules equals M. What's M? Well, M is the mass of air, 200 grams. We need it in kilograms. Kilograms, kilojoules. So that should be 0.2 kilograms times 1 times delta T. So we rearrange this equation and we get delta T equals 750 divided by 0.2, and that equals 750 divided by 0.2, 3,750, 3,750. Increases by, the temperature increases by 3,750 Kelvin, or degrees Celsius. It's an increase. The oxide, that's a phosphorus oxide, so we're looking at phosphorus oxide, formed in the reaction, contains 43.6% phosphorus. Well, the rest is oxygen, so it must be 56.4% oxygen. How do we work out the empirical formula? We must divide each one by its own relative mass. So for phosphorus, we've got 43.6 divided by the relative mass of phosphorus, which is about 31. We should look it up, really, but I'm not going to do that. 43.6 divided by 31, and that comes to 1.406. 1.406. And for oxygen, it's 56.4 divided by 16. 56.4 divided by 16, and that comes to 3.525. 3.525. Well, that's horrible. Look at that. Look at those. Those two numbers. We can't do anything with these, can we? Yes. What we can now is we divide both by the smallest. Divide through by the smallest. And we get, for phosphorus, it's 1.406 over 1.406, and that equals 1, clearly, because it's the smallest. And the oxygen is 3.525 divided by 1.406. This is where we need the calculator. 1.406, and that comes to 2.5. Alright, so we should be able to see that now if we double both, that will get rid of that will give us P2O5, and that's the empirical formula. I want to put an equal sign there to show that this is the empirical formula. P2 Alright, so you've got 3 marks for carrying out this operation. Whoop. Now the molar mass of this oxide is 285, so what we need to do now, if we want to determine the molecular formula, well, we look at the mass of the empirical formula equals, well, it's 31 plus 31 for the 2 phosphoruses, plus 16 times 5. Alright, so we'll do it like this. This is the empirical formula mass. What does this come to? Well, 5 16s are 80. 80 and 62 is 142. We can see that the molecular mass is bigger than the empirical formula mass. So how many times bigger? Well, so we divide 285 by 142, and it comes to near as damn it 2. So that means there are 2 empirical formulas. So the molecular formula equals 2 times the empirical formula. Empirical formula, which equals P4O10. I'm going to make it a nice blue colour so we can see it's the answer. Right, state the equation for the reaction of this oxide, P4O10, of phosphorus with water. Well, this is something we have to learn. It's all part of the reactions of oxides with water, so P4O10, let's put it in there. And we're reacting it with H2O, H2O. What does it give? Well, we need to know really that it gives the acid which has phosphorus in the 5 oxidation state, which is H3PO4. Now we have to learn this formula for phosphoric acid. Like sulfuric acid is H2SO4, phosphoric acid H3PO4. We have to learn it. Now we have to balance this equation. Well, there's 4 phosphorus atoms there, so we must have to put a 4 there to get 4 phosphorus atoms. Now there's 12 hydrogens. We've got to put a 6 there to get 12 hydrogens. Let's check the oxygens. 10 oxygens there and 6 are 16. 4 4s are 16. This is balanced. Next question. 2.478 grams of white phosphorus was used to make phosphine according to the equation. Right, so there's phosphine. There's the equation. 1 phosphorus molecule plus 3 hydroxide ions. First of all, though, we just need to know how much phosphorus is used. Well, we need to divide this, which is the mass, because moles equals mass over relative mass. So it's mass. And what's the relative mass? Well, it's 4 times 31. 4 times 31. So yes, 4 times 31. 4 times 31. What does this come to? Well, 4 times 31 is 124, so it's 2.478 divided by 124, and that comes to 0.01998, which is 0.02 moles. But the phosphorus reacted with this. So we can work out the moles of sodium hydroxide. Moles of NaOH equals, well, this is molarity times volume. Molarity is 5. Volume is 0.1. So that comes to 0.5 moles. So we have, on one hand, we've got sodium hydroxide 0.5 moles. We've got phosphorus 0.02 moles. And how much sodium hydroxide would be needed? Well, from the equation, 0.02 moles of phosphorus needs 0.02 times 3 moles of sodium hydroxide, and that equals 0.06 moles. Well, you can see that there is the sodium hydroxide is in NaOH is in great excess, hence the limiting reagent is phosphorus. And there we show the limiting reagent, phosphorus. Making those, I forgot to make this one nice and blue here, didn't I? There we go. Alright. Now we have to determine the excess amount of the other reagent. Well, like I said, we've shown how much is needed, 0.06, and we've got 0.5, so the excess is 0.5 minus 0.06, which comes to 0.44 moles. The bit that's left over, if you like. The excess is what's left over after the reaction. Now we have to determine the volume of phosphine at standard temperature and pressure that was produced. So what we need to know is to go back to our equation. We need to know there's 1 mole of phosphine is produced for every mole of P4, the limiting reagent. So here we can say moles of phosphorus equals moles of phosphine. So we know how many moles of phosphorus we've got, 0.02. Now we have to use our equation for getting the volume, PV equals nRT. What do we want? We've got N, we know T, we want V. Alright, so V equals nRT over P. Now at standard temperature and pressure, I could cheat here. I could say, well, I know that the molar volume is 22.7 litres. Or else we could go straight forward and calculate it. We could say V equals, well, number of moles, 0.02, times 8.31 times standard temperature and pressure, so that's 273, divided by standard pressure. Pressure is 1.0 times 10 to the we're going to do this in kilopascals, so we do times 10 to the 2. Well, let's just write it as 100. It's easier, isn't it? 100. Now don't forget, if you use kilopascals for the pressure, then you get your answer in litres. Alright? So then we do this calculation. We've got 0.02 times 8.31 times 273 divided by 100, and that comes to 0.454 V equals 0.454 litres, but we want to know the answer in centimetres cubed, so of course we must multiply that by 1000, so it comes to V equals 454 centimetres cubed. Let's get the indexes correct, just to make it look attractive. Let's make all that nice and blue to show it's an answer. And let's push on to the next question. The question is about the energy of propanol. Gaseous propanol burns as shown by this equation. There's the equation for the burning. Everything's a gas, so we can use bond enthalpy terms to calculate the energy change when all the bonds bonds shown are broken. Right, well, let's count them up. 1, 2, 3, 4, 6 carbon-hydrogen bonds, 2 carbon-carbon bonds, and a carbon-oxygen bond. Alright, so our equation should just show 6 times CH, which is 413. It should show 2 times 347. It should show 1 times 736. And we're going to add them together. Well, perhaps we'll work them out first, then we'll add them together, shall we? 6 times 413. 413 times 6. That comes to 2478. 2478. 2 times 347. 347 times 2 equals 694. Let's get them aligned. And 1 times 736. Well, that's pretty difficult, isn't it? Comes to 736. Now we're going to add all of these together. And what do we get? Let's have a look. 694 plus 736 plus 2478. 2478. Two carbon-carbon bonds. 2 carbon-carbon bonds. I'm just checking it through. 1, 2, 3, 4, 5, 6. Well, it makes 3908 equals 3908 kilojoules. I know, we've forgotten the 4 oxygens, haven't we? I knew there was something wrong. We haven't included the 4 oxygens. That's very bad of me, isn't it? 4 times 498. This is something that quite often happens. People they spend so much time working on the organic bit, they forget that it's reacting with oxygen. So that's wrong. 4 times 498. 1992. 1992. We add them together. Now, when we add them all together, let's have a look. 1992 plus 736 plus 694 plus 2478, and that comes to 5,900. I recognise that number. That's the enthalpy change which occurs when all the bonds are broken. So this is endothermic. It's a positive value. Now we'll do exactly the same. So let's just make it blue, so it's obviously the answer. Oh, let's take the next part of the question. All the bonds formed here are formed. Well, 3 H2O's have got 6 OH bonds. 3 CO2's got 6 CO bonds. That's easy. So it's 6 times the OH bond energy, which is 464, equals 6 times 464 equals 2784. 2784, and 6 times C double bond O, 736. 736 equals 736 times 6, 4416. Add these together, and we get 4416 plus 2784, 7,200. But this is negative 7,200 because this is the energy released when bonds are formed. I seem to have an issue with fonting here, so let's get rid of that underlined style. We don't want that, do we? No, of course we don't. And let's make it nice and blue. Alright, so bond breaking, bond making. And clearly what's going to be asked now, we're going to use the answers to calculate the standard enthalpy of combustion? Well, it's simply 5900 minus 7200, and that's going to come to negative 1300 kilojoules. More VSEPRT, more valence shell electron pair repulsion theory. Let's have a look. What does this ask us for? It can be used, the theory can be used to predict the distribution of electron pairs and shapes and bond angles of many molecules. Now, show how the theory can be used to explain why ammonia has a tetrahedral distribution. Right, okay, so we need to say nitrogen has got 5 valence electrons. Electrons. 3 hydrogens provide 3 valence electrons. So our total, what's our total? Well, what do we get when we had 5 and 3? Total 8 valence electrons, and this is 4 pairs. 4 pairs equals 4 domains. Now 3 domains are used, 3 pairs are used for bonding, leaving 1 lone pair. So the molecular shape, well, first of all, the electronic, now let's put the electronic shape in here, 4 domains equals tetrahedral. Tetrahedral, and this has got a bond angle of 109.5. 3 leave 1 lone pair. The lone pair now, this lone pair, if the 3 pairs are used for bonding, so this gives us a molecular shape of trigonal pyramidal. The lone pair now, the lone pair repels bonding pairs more than bonding pair repulsion, and this squeezes the angle to 107 degrees. Alright, so that's our full explanation. So we've explained why we've got the shape from the number of valence electrons, the electronic organization, the molecular shape, and the final result of the lone pair repulsion. Let's do the same thing. I'm going to copy this because it's almost identical, in fact, for this question, except here we've got phosphorus is also in group 15. Phosphorus has got 5 valence electrons. 3 bromine atoms each provide 1 valence electron, so that's 3 valence electrons. So the total is 8 valence electrons, 4 pairs, 4 domains, tetrahedral, bond angle, 3 pairs used for bonding, blah 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 blah. It's exactly the same. So the bond angle squeezes to, it would just say, should we say less than 109, and that would fulfill this question as well. Explain why Br3 is polar. Well, the individual Br bonds are polar. And in the molecule, the individual dipoles do not cancel out. And that explains overall it must be polar. If the individual dipoles don't cancel out, well, you've got overall polarity. Question 8. I think this is the last question, is it? Okay, so we've got a student that's adding hydrochloric acid in 5 centimeter cubed portions to 1 mole of sodium hydroxide. And there's the results. So as we're adding, it's heating up, and then it seems to go down again. So presumably this is an effect of adding cold liquid to another hot liquid. It's cooling it down. But we don't know exactly where the changeover is. So what's the first stage? We have to write an equation for the reaction of sodium hydroxide with hydrochloric acid. NaOH plus HCl. This is a straightforward neutralization reaction. NaCl plus H2O. It doesn't even require balancing. It should be done in your sleep, this reaction. Now, next part, what do we have to do here? By drawing appropriate lines, determine the volume of hydrochloric acid it requires. So appropriate lines, well, it's telling us we have to draw lines, not a curve, lines. So let's have a look. Let's draw some lines. Well, here, if we try to draw the line of best fit here, and the line of best fit, it's a bit by eye, but there we are, here. Well, what does that give us? Well, that tells us, that shows us here is more or less and where the two lines cross. We can see that this is 20.8 and here this is 30.4. Right, so 20.8 and 30.4 by drawing the lines. It's 20 point, is that 20.8 or 28? It's 28, it's not 20.8, it's 28 centimeters cubed. 28 centimeters cubed of hydrochloric acid is needed to completely neutralize. So the concentration of the hydrochloric acid, well, we've got MaVa equals MbVb, because the moles must be equal when they're completely neutralized. And we know the sodium hydroxide, the MaVa, we know Va, so we've got Ma, the molarity of the acid, will equal to, actually I'm not going to put an equal sign there, Ma, the molarity of the acid must equal MbVb over Va. What are we adding to what? We're adding we're adding acid to the sodium hydroxide. The sodium hydroxide concentration 25 ml of 1 molar. So Ma, the molarity of the acid, equals, well, Mb is 25, sorry, Mb is 1 times Vb is 25 divided by Va, volume of acid, 28. You can use 25 and 20. I didn't need to change these into litres because their units cancel out anyway, so I could just use this in centimetres cubed. And it comes to 0.893. Molarity of the acid, 0.893 moles per litre. It does say include units here, so it's very important that we do include units because it's a 2-mark question. So if you miss the units out, you're going to lose a mark. Determine the temperature change. Well, we said it went up to 30.4 started at 25, so the temperature change is 25 minus 30.4. Is that right? Not really, it should be the other way around, shouldn't it? 30.4 minus 25, not difficult, it's 5.4 degrees. 5.4. So the enthalpy change for the reaction, well, once again, back to our E equals MC. I just need a delta sign. Symbols. Yeah, MC delta T. So energy change. Well, the mass. Well, here we've got 25 centimeter cubed mixed at the neutralization point. There's 25 centimeter cubed of base mixed with 28 centimeter cubed of acid. Let's assume they both have a mass of 1. So here it will be, well, let's just show you that my working. 0.025 plus 0.028. This is the mass in kilograms. Times 4.18 for the specific heat capacity of water, times the temperature change, 5.4. This will give us our energy in kilojoules. Right, so we work this out. So it's 0.053 times 4.18 times 5.4, and that comes to 1.196. 1.196 kilojoules, but this isn't for a full mole. We have to work it out in kilojoules per mole. So now we have to divide by the number of moles of sodium hydroxide used. Right, so the energy per mole equals 1.196 divided by 0.025. That's the moles used, because it's 25 centimeters cubed of 1 molar solution. And that comes to 47.85. 47.85 kilojoules mole minus 1. Let's make it pretty. There we are, and let's blue it up because it's an answer. The accepted value from the literature is minus 58. Oh, don't forget, we forgot the negative sign. It's an exothermic reaction. Mustn't forget the negative signs for exothermic reactions. It reminded me when I saw the negative sign there. Calculate the percentage error between this, your value, and this value. Well, first of all, we work out the difference. Now, we don't need to work in negatives. We can work in positives. That won't make any difference because we're working out a percentage error. So it's 58 minus 47.85, and that comes to 10.15. And we divide this 10.15. The difference is divided by the actual value, 58, and then we multiply that by 100 to make it into a percentage. So our percentage error is 17.5%. Now just to finish off, last question. Suggest the major source of error in a calorimetry experiment. What's the major source of error in a calorimetry experiment? Heat loss to the environment. Can't spell. How could we reduce this? Use an insulated container. There we are. Nice and easy answer for the test. And that's all there is to it. Bye.